This screencast is going to look at t-tests. We will look at how to test the assumptions of t-tests, how to run and interpret independent and paired samples t-tests, and how to report the findings of a t-test. The first test we're going to look at is an independent samples t-test. This is where we have two groups, which is our independent variable, which are measured on one dependent variable. The groups could be naturally occurring, such as sex differences, so male or female. They could also be designed by the researcher, for example, an experimental and a control group, or they could be created from a continuous variable, for example, creating high and low groups from a variable which we've measured. For more information on how to create groups of a continuous variable, please refer to the data restructuring screencast. So in the following example, we're going to look at sex differences, which is our group, in mean levels of cognitive anxiety. So are there differences between males and females in their levels of cognitive anxiety? Before we run the test, we need to check that we've met the assumptions of an independent samples t-test. First assumption is that the samples are randomly selected from population. In the present example, we have to assume that this has been met, but this is something we have to consider when conducting our research. The dependent variable must be measured on an interval or ratio scale, which in this example is measured on a 1 to 5 questionnaire-based scale, so satisfies that assumption. The independent variable must be a dichotomous variable. This means that a variable has two distinct and mutually exclusive categories. You can only be in one category, you cannot be in both. So you can see, looking at the data, that in the sex, the values are labelled 1 or 2. By switching to the variable view, we can look at what these values mean. By clicking on the values box for the sex variable, we can see what the labels 1 and 2 mean. So we can see that males have been labelled 1 and females have been labelled 2. This shows that we can say that we've satisfied the assumption that we have mutually exclusive groups. You can only be 1 a male or 2 a female. You cannot be in both groups. The next two assumptions we need to check using the Analyze tab and the Explore function of SPSS. The two assumptions are that the number of samples in each group will not be hugely different from the other, ideally not with a group that has more or less than 20 people than the other group. Also, we need to check that the scores are normally distributed. So, if we select the Analyze menu, go to Descriptive Statistics, and then select Explore, we can test both of these assumptions. As we said before, in this example, cognitive anxiety is our dependent variable and sex is our independent variable. So to explore the data, we're going to select cognitive anxiety and move it to the dependent list. Next, we're going to select our independent variable of sex and move this to under the factor list. Factor is often used as another word for independent variable. Next, we're going to click on the Plots box and then select Normality Plots with Tests. We click Continue and then click OK to run the Explore function. On the output, we can see on the first box that there are 8 males and 7 females in this example. Therefore, we can say that we've satisfied the assumption that the sample sizes of the two groups are not hugely different from each other. If we scroll down, we can look at the normal QQ plots for males and females on cognitive anxiety. On the plots, each circle represents an individual score of cognitive anxiety, and what we want is that all the scores are clustered around the line. And as you can see, for both males and females, this is the case in the present example. Therefore, we can assume that our data is normally distributed. And if we scroll back up to the tests of normality, we can see that for both tests and for both males and females, the significance values are above 0.05. So they are non-significant, which is what we want when we're looking at our distribution of our data. Therefore, we can say that we have met the assumption that our data is normally distributed. So far we've met all the assumptions required to run an independent samples t-test. The final assumption is that the variances of both groups should be approximately equal. That is, that the spread of the scores around the mean is approximately the same in both males and females. This is tested using the Levine's test, which is done at the same time as the main t-test analysis, which we will run now. To run the t-test, we're again going to go to the Analyze menu. This time we're going to select Compare Means and select Independent Samples t-test. In the box, the test variables is another word for the dependent variable. So in this example, we're going to select cognitive anxiety, which is our dependent variable, and move it into the test variables box. The grouping variable is our independent variable, so we're going to select sex and move this to the grouping variable box. We then need to define the groups, so tell SPSS which groups we would like to analyse the data from. In our example, we only have 2 groups, but there may be times where you have more than 2 groups, yet you only want to look at differences between 2 of them. And when defining the groups, we need to use the same numbers that we used when coding or labelling our gender groups. So in group 1, I'm going to put 1, which is for our males, and group 2, I'm going to type 2, which is the females. Click Continue, and then click OK to run the t-test. At the top of the output, the means and standard deviations for males and females' cognitive anxiety are displayed. Next, we want to look at the Levine's test of equality of variances. As you can see, the significance value is over 0.05. This tells us that there are no significant differences between the variance of male and female cognitive anxiety. So that meets our assumption that the variances of the 2 groups are approximately equal. Because of this, we then look at the equal variances assumed line for the main t-test interpretation. If the significance value is below 0.05, indicating that the variances are significantly different, we would look at the equal variances not assumed line. If we scroll across, we can look at the values under the t-test for equality of means. The first values we're going to look at are the t-statistic and the significance value. The t-statistic is minus 0.131 and the significance value is 0.898. As this is above 0.05, this means that there are no significant differences between males and females in their scores of cognitive anxiety. The t-statistic is negative because the group with the higher code, so 2 is females, has higher cognitive anxiety. If the groups were coded as females being 1 and males 2, the t-values would be identical but would be positive. For the 95% confidence intervals, the lower value is minus 0.093 and the upper value is 0.97. This means that if we took 100 randomly selected samples from the same population as this one, for 95 of them, the mean difference would lie in between these two values. In this example, we've used a two-tailed test, as we did not have a clear hypothesis about which group would have higher cognitive anxiety. If we had a sound theory or evidence based on previous research where we expected one group to be higher than the other, we could use a one-tailed test. To get the probability value for a one-tailed test, we would divide the probability value given by SPSS, the significance value, by 2, and this would give us the significance value for a one-tailed test. From the results of the t-test, we can conclude that there are no significant differences in the means of cognitive anxiety between males and females. When writing up our results, we need to report the means for both males and females' level of cognitive anxiety, and also the t-statistic, the degrees of freedom, and the p-value. So for this example, we've reported that males had lower cognitive anxiety than females, and given the mean for each group, but that this difference was not statistically significant, with a t-value of minus 0.13, 13 degrees of freedom, and a p-value of 0.90. It is worth remembering that when we write up results in our results section, we generally report values to 2 decimal places. Next, we're going to look at how to run a dependent samples t-test. This is where we have one group who are measured over 2 different time points. For example, we might want to look at endorphin levels in a group of runners before and after a race to see whether there has been a significant change in their endorphin levels during the race. In this dataset, we have the B endorphin levels of 11 runners before and after a race. Before we run the dependent t-test, we need to check the assumptions of a dependent samples t-test. These are similar to some of the assumptions of an independent samples t-test. For example, we need our dependent variable, in this case endorphin levels, to be measured on a ratio scale, which in this case it has been. The assumption of equal variances does not apply to dependent samples t-tests. Finally, we need to check that the difference in between the before and after scores are normally distributed. To do this, we have to create a variable using the compute function. So, we go to transform and select compute. The first thing we need to do in the compute box is name our variable in the target variable box. Therefore, I'm going to write difference in this box. Next, I want to create our numeric expression. To check the normal distribution, we need to subtract the after scores of the endorphins from the before scores. So to do this, I'm going to move before into the numeric expression box. I'm next going to select the minus sign. Then I'm going to select after and also move this to the numeric expression box. This has created a formula which will subtract the after scores from the before ones. If we then click OK, we can then see that a difference variable has been created in our spreadsheet. We now need to check that this variable is normally distributed. To do this, we go to Analyze, select Descriptive Statistics, and then choose Explore. In the Explore menu, I want to move the difference variable that I've just created into the dependence list. As this is a dependent samples t-test, we only have one group, so we don't need to move anything into the factor list. Next, select plots. And in this box, we want to select histogram, normality plots with tests, and deselect stem and leaf. Click continue, and then OK to run the Explore. The first box we want to look at is the descriptives box and the skewness and kurtosis values. As mentioned in previous screencasts, we want the ratio between the statistic and the standard error for both skewness and kurtosis to be less than 1.96. In this example, it appears that these values are both less than 1.96, which suggests we can assume that the data is normally distributed. If we look at the test of normality, both the Kolmogorov-Smirnov and the Shapiro-Wilk values are non-significant, again suggesting that our data is normally distributed. It is worth noting that in larger sample sizes than the present example, these tests are particularly sensitive and may show that the data is not normally distributed when in fact it is. In these examples, it is worth paying attention to the histogram, box plots and normal Q plots, which we will go on to discuss. The histogram also suggests that the data is normally distributed, and the normal QQ plot shows that in general all the points are clustered around the diagonal line, again suggesting that our data is normally distributed. The final indication that our data is normally distributed is that the box plot has not identified any outliers or extreme values. Now we are satisfied that we have met the assumptions of a dependent samples t-test, we can actually run the main test. To do this, we go to Analyze, select Compare Means, and choose Paired Samples t-test. In this box, we want to select the before and after variables and move them into the Paired Variables box to tell SPSS that these are the means we want to compare. Once we've done this, we can click OK to run the t-test. The first box in the output gives us the descriptive statistics for the before and after variables. Here we have the means, standard deviations, and standard error of the means for both variables. As we can see, the mean for the beta endorphin level after the race is 27.16, which is a lot higher than the level before the race, which is 8.43. However, we can't tell if this difference is significant without looking at the t-value and its relevant p-value, significance value. If we look at the t for the difference in between before and after the race, the t-value is minus 7.46 and the significance value is 0.000, so this is less than 0.001. As this is below 0.05, we know that the difference between the beta endorphin levels before and after the race in this group of runners is statistically significant, with the levels being significantly higher after the race. The 95% confidence intervals tell us that if we took 100 randomly selected people from the same population as we've tested here, the difference in between their scores before and after for 95 of these 100 would lie in between minus 24.33 and minus 13.14. From the results of our dependent samples t-tests, we can say that beta endorphin levels are significantly higher after a race than before a race in runners. This concludes the screencast for t-tests, where we have looked at both independent and dependent samples t-tests. We have shown how to check the assumptions of these tests, how to run them, and also how to interpret and report the analyses.